Hey everyone, it's a pleasure to be here speaking to you. Today I'm here to talk to you about best practices when building serverless applications with .Net and AWS Lambda. So let's start with a number, 493 milliseconds. What do we think that number is? Well, whenever I talk about .Net and Lambda, the first thing that almost always comes up is cold starts. So I thought I'd tackle this one nice and early on. 493 milliseconds is the P99 execution time, including a cold start, we have seen when using .NET 6 and a native AOT compiled .NET Lambda function. This is faster than TypeScript and similar to Golang when using a comparable application architecture. A far cry from the almost 2 seconds that has been seen historically and what most .NET developers I speak to associate with Lambda. We'll come back to this later on, but I just thought I'd get this out of the way nice and early. So how many of you listening spend time operating your application instead of writing code? When I say operating, I mean managing servers, setting scaling policies, or worrying about whether your auto scaling groups will move quickly enough to hit a large unexpected load. This is time spent when you're not delivering value to your customers. Whilst how well you can auto scale may give you a slightly better customer experience, what your customers care about the most is the unique feature that led them to your application in the first place. Now, just imagine for a moment what it would be like to build applications in a world where all you had to worry about was your application code, your business logic, solving the complex problems that made most of us want to be developers in the first place, not patching Windows servers or managing how well your Kubernetes cluster can scale. Well, with serverless, you can, and that's what we're going to get into today. So who am I? I'm James Eastham. I'm a professional services consultant at Amazon Web Services. So by day, I'm helping AWS's customers build applications on AWS. But by night, I'm a lover of all things .NET and serverless. I love enabling people to build scalable, resilient applications using .NET and serverless technologies. And today we're going to look through a few different topics. We're going to first take a step back and start with why do we need serverless? Where did serverless come from? Then we'll level set on what exactly AWS Lambda is. And then we'll go through a few different steps with running .NET on Lambda, from running an existing .NET Core API on Lambda to developing single-purpose event-driven functions. And then we'll actually walk through the software development lifecycle and some best practices and optimizations you can start to look at when you're building .NET functions on Lambda. But as I said, let's start and just take a step back for a second. So if I think back to the first job I had in tech, it was an e-commerce company in the north of England, and their systems ran from a server room within the office. From memory, I think there was about 10 servers, maybe. And I recall an outage we once had that caused absolute panic because systems were going offline, customers were ringing up, but nobody had actually changed or done anything. Nobody could work out what had happened. It actually turned out that someone had accidentally knocked out an Ethernet cable from one of the boxes in the server room. Panic over. But there's no way we could have preempted that. That was just an accident that happened. And I'm sure we've all got similar stories from running applications on physical machines in data centers. So we took a step forward with the cloud, and the cloud started to help with some of that. I've worked with customers who maybe take their Windows workloads and run them on EC2 instances with auto scaling groups across multiple availability zones in AWS. In conjunction with auto scaling application servers, maybe they deploy the database across multiple availability zones as well. So if an availability zone goes offline, the application can continue to function. We could even architect the most critical applications to run across multiple AWS regions. So that was all possible. The cloud started to enable that with EC2. But EC2 auto-scaling does have some challenges because auto-scaling needs a scaling policy. So what metric do I use to to perform that scaling? And also, how quickly will my new instance get scaled? Well, it will scale as quickly as it takes for the original instance to fail a health check, for the new instance to be initialized, and then for the new instance to be added to the auto-scaling group, and also then pass a health check. If we think back to my on-premise servers, this is so much better than running an on-premise server, but it is still challenging to have good health checks if you're building applications on EC2. So what does it mean for a server to be healthy? Even that is a difficult question. Is it a system-based thing? If the network goes offline, if the server just stops responding, or maybe there's some metrics around your instance, the memory is exhausted, or there's some corruption in the file system. It's really difficult to start to get an auto-scaling policy that's accurate for then you to suddenly at some point in the future receive an unexpected load that your auto-scaling policy just didn't plan for. We use this quote a lot at Amazon: everything fails all the time. If you've been working with AWS, you'll have heard Werner Vogels say this, and systems and applications can experience failure in a large number of ways. Power can fail. Someone can accidentally knock out an Ethernet cable. You might deploy a new version that has a memory leak. There's always the possibility for things to fail. And when we think about failure at AWS, we actually have a pillar as part of our well-architected framework around reliability. And we're going to use this, I want you to keep this reliability pillar in mind as we talk about Lambda. If you're building EC2 or even container-based workloads, you need to consider a lot of these points: recovery, scaling, capacity management. All of that needs to be understood and maintained by either you as the developers or some kind of platform team. This is undifferentiated heavy lifting. It isn't making your business stand out. With serverless, a lot of this comes for free. If you're running your compute on AWS Lambda, you don't need to worry about that underlying infrastructure at all. Scaling, capacity management, failover, multi-AZ, all of that is handled by the Lambda service. You don't need to worry about it. That is for us to worry about, for AWS to worry about. And it comes down to the operational responsibility model, the shared responsibility model at AWS. And as we shift towards a more serverless world, you as the developers start to take on less and less responsibility. If we go to the far left of this diagram, that's the company I used to work for, with the single set of servers sat in a server room. There's a lot of operational responsibility there and a lot of potential for failure. As you move over to the right and start to shift towards things like Fargate and AWS Lambda, AWS is taking on more and more of that responsibility. That enables you as the developers to focus only on your business logic and the things that will delight your customers. And this same responsibility shift can apply at all levels of the stack. We're very focused on compute and Lambda today, but your databases, you can use DynamoDB, that has that same failover auto scaling. S3, EventBridge, SQS at all levels of your application stack. There is this possibility to shift more and more responsibility on to AWS. Okay, so what is AWS Lambda? Before we dive into the .NET specifics, I just want to level set for a moment and just make sure we're all on the same page for what AWS Lambda actually is. So Lambda's biggest superpower is that it's completely event driven. Lambda reacts to things that are happening in your system. And it does that without you provisioning or managing any servers. You only pay for the compute time you consume, and there's no charge when your code isn't running. That compute time is charged on a per millisecond basis, and that per millisecond charge changes based on the amount of memory that you allocate to your function. It's important to note with that point that even though you assign more memory to your function, and therefore there's a higher per millisecond cost, the overall cost of your Lambda may be less, because if it executes in a tenth of the time, that's going to cost you less overall. And with Lambda, you can run code for virtually any type of application or backend service, all with that zero administration. Lambda just takes care of everything required to run and scale your code with incredibly high availability. You can set your code up to automatically trigger from other AWS services, or you can even call it directly from the AWS SDK. You can write Lambda functions in a range of natively supported languages, one of which is .Net. And then you can package your code in either a zip file, up to 250 meg unzipped code, or you can even use container images up to 10 gigabytes in size. Between them two options, it gives you the capability to run almost any workload using Lambda. It's incredibly powerful. So Lambda gets invoked in a few different ways, and there's 3 different ways that a Lambda function can be started. The first is a synchronous invoke. A synchronous invoke is how it works with things like API Gateway. API Gateway will pass the HTTP request to Lambda as a payload, and the API Gateway will then wait for the Lambda function to do its work. The response of the Lambda function will get passed back to API Gateway, and API Gateway will return a response to the caller. There's also, if you're using the SDK, there's a synchronous invoke method on the SDK, which will do the same in your application code. The second model for invoking a Lambda function is the asynchronous model. And the asynchronous model is where the Lambda service manages an internal queue of requests. And if you call a Lambda asynchronously, your request just gets placed on this internal queue, and you can continue doing other work. And the Lambda service will manage the processing of them requests. This is how it works with things like Amazon SNS. If SNS sends a message to Lambda, SNS doesn't wait. It just sends the message and carries on and does something else. And then Lambda will work through that list of requests. Ordinarily, that's very quick, and you can actually monitor that wait time using X-ray. And the final method of invocation is the poll-based mechanism, and this is actually one of the most powerful. The poll-based invoke method is where the Lambda service will poll services on your behalf. Things like SQS, DynamoDB streams, and Kinesis, that is all a poll-based invoke method. The reason that's powerful is that the Lambda service will manage the retrieval of records from the queue. It pass that as an event payload to your function. Your function can do the work, and the Lambda service will also manage deleting that message from the queue afterwards. And the same applies for DynamoDB streams and Kinesis streams. The Lambda service will keep track of the last record read. So it's incredibly powerful. Okay, so how does Lambda actually work? What does it do under the hood? Well, whenever Lambda receives an invoke request, that always comes into a front-end service. And that front-end service is going to look for an execution environment that your function can be running. Execution environments are reserved for a specific function version, and they can't be reused across different function versions or accounts. So an execution environment is completely segregated from other execution environment. Each execution environment can only be used for one invocation at any one time. So if you were to get 2 requests in at the exact same time, you would likely end up with 2 separate execution environments. Now, how are these execution environments created? So when the request comes in for a given Lambda function, the Lambda service will look for an existing execution environment that isn't already processing a request. If there are no execution environments available, it will then go and create a new execution environment. And this is what we know as the initialization phase of a Lambda function. The initialization phase is where the execution environment is being created, the runtime is being loaded in the case of .NET, your function code is being downloaded either from S3 if you're using zip files, or from ECR if you're using containers, and then your code is bootstrapped, so your code is started up. That is what we know as a cold start. If there is an execution environment already available, the Lambda service will just pass that payload straight to the existing execution environment, and that's what we know as a warm start. So that's where the latency comes from when you're running a cold start, because that execution environment needs to get created. There's also a feature in Lambda called provisioned concurrency, which is where you can pre-provision a certain number of execution environments that will always be warm and waiting for you. And that means if you have a steady state load, or you know the kind of load that you're going to expect, you can meet that load without any cold starts. One thing to bear in mind with provisioned concurrency is that your Lambda functions will then not scale to 0, which means you will still have an ongoing cost even when your code isn't running. Okay, so as we start to migrate .NET applications to Lambda, a lot of .NET applications use more traditional relational databases, at least the more legacy applications that I've worked with. And that means that you need to connect your Lambda function to your VPC, to resources within your network. So understanding how networking works in Lambda is really quite important. So your Lambda functions will always execute within a Lambda service VPC. So that will always be completely separate, a separate account to your account. If you need to access resources within a VPC in your account, you can then set a subnet and security group on your Lambda function when you deploy it. And what that actually does behind the scenes is that actually deploys an elastic network interface into the subnet that you define when you deploy your Lambda function. So you'll have an ENI then in your account, and that ENI creates the connection from a VPC to VPC, that gateway in the Lambda service, to the ENI in your network. And that means now all of the network traffic coming from these Lambda functions will then route through that ENI into your network. There's a couple of really important things to remember when you use Lambda in this way though. Because it deploys an ENI into a subnet in your account, that will use up an IP address from the available IPs in the CIDR range of that subnet. So that will only ever be one IP per Lambda function. That's not per execution environment, but that will take up an IP address. If you exhaust all of the IPs in a subnet, you won't then be able to deploy new Lambda functions. And the other really important thing to remember is around routing and network routing. So if you need to access maybe a public API or services like S3 or DynamoDB, then you'll need to ensure you've got a route from that subnet where your ENI is out to either S3 and DynamoDB, maybe using a gateway endpoint, or out to the public internet using an internet gateway. So that's really important to remember. I've once spent hours trying to debug an issue with a Lambda function timing out, only to realise that I had a call to a third-party API and I'd forgot that there was no route out then from my subnet to the public internet, and it just timed out my Lambda function. So that's really important to understand. Okay, let's start talking about .NET now. It's enough talking about the theory, let's get into the specifics. So .NET on Lambda currently supports 2 managed runtimes. That's .NET 6 and .NET Core 3.1. An important thing to point out, given that we're in September 2022 now, is that in December .NET Core 3.1 will go out of support. And at that point, we'll start to depreciate the .NET Core version on Lambda. And when we depreciate a runtime, that happens in 2 phases. The first phase is that Lambda no longer applies any security patches or other updates to the runtime. And you can no longer create new functions that use that runtime, but you can continue to update any existing ones that you have. The second phase of the depreciation is where we prevent you from creating or updating functions that use the depreciated runtime. To update your function once we're in phase 2 is you need to actually migrate to .NET 6. But I'd actively encourage a lot of you to migrate to .NET 6 as soon as possible, because there are a lot of performance benefits that come from doing that. .NET on Lambda supports both x86 and ARM-based architectures, and when you define your Lambda function, you can define a couple of different things. So the first is your memory allocation. So you can allocate memory from 128 meg to 10 gigabytes to your Lambda function, and the CPUs you get is allocated proportionally to the amount of memory that you define. Lambda functions can only run for a maximum of 15 minutes, but you can actually tweak that to be even lower, so you could set that from anywhere between 1 second and 15 minutes. And as we talked about when we looked at the execution models, it supports both synchronous and asynchronous invocations. Okay, enough about Lambda. Let's actually get into running .NET applications on Lambda now. And we're going to go on a little bit of a journey to do this. And we're going to start from where a lot of you might be today. We're going to start from an ASP.NET API. And I speak to a lot of developers who aren't actually aware of this, but it is possible to run a .NET Web API in Lambda with little to no code changes. In fact, with the out-of-the-box .NET Web API template, we can make it Lambda ready in 3 simple steps. So let's start with that .NET Web API created from the .NET CLI template. And as I'm sure a lot of you know, when you're building .NET APIs on Lambda, there's 2 key components. There's the controllers, the actual endpoints of your API, and then your startup class or your startup logic. Controller classes are where your API endpoints are defined, and your routes and methods on that controller class are defined using attributes, HTTP GET in this example. And any dependencies are injected through the constructor. All the configuration of that dependency injection and any maybe loading of secrets, setting up connection strings, all of that is done in your startup class. So what we're going to do with this now is going to take this API and actually run it on AWS Lambda exactly as it is with no code changes at all. So to do this, there's a couple of additional things that we need to add. Remember, we're not changing the existing code, we're just adding some additional things. The first is a reference to the Amazon Lambda ASP.NET Core Server package. And that package makes it really easy to then run your API behind either API Gateway or an application load balancer. The second thing you need to do is potentially make a slight update to your project file. So there's a couple of flags that Lambda needs to be able to run your .NET code. The most important one is the generation of runtime configuration files. So you need to make sure that generate runtime configuration files flag is set to true. And the final addition, and this is the one where all the magic happens, is adding a new class to your project. This class will be the entry point that the Lambda service uses. The name of this class is unimportant. I mean, it normally makes sense to use something like Lambda entry point, so it's obvious, but what is important is the base class that it inherits from. And that base class you inherit from will change based on what you are putting in front of your Lambda function, whether that's API Gateway or an application load balancer. In this instance, where we've got our Lambda function sat behind an API Gateway HTTP API, so we inherit from the API Gateway HTTP API v2 proxy function class. Yes, that is a little bit of a mouthful. All of these base classes include a method called function handler async, and that will be the method that the actual Lambda function invokes. When we set the handler of our Lambda function, that will be the method that we use. And it's in this method where all the magic happens, because this is where we convert the event payload that comes in from API Gateway, and that will just come in as a JSON string, and we convert that to a format that the ASP.NET Web API can understand. When the ASP.NET Web API then returns a response, then that same class will convert that response back to a format that API Gateway understands. And that's why you need a different base class based on what is in front of your Lambda function, because that request and response payload will be slightly different. The final thing we need to do is, if we're using API Gateway, it's just to add a single route to our API Gateway, which is what I'd call a greedy route, that will match all paths and all method types, and that will then pass all of our requests onto our Lambda function, and then our Lambda function will handle the routing to the right endpoint. There are trade-offs to running your .NET APIs in this way. The Lambda lith can be considered a little bit of an anti-pattern, but I think there's some really convincing use cases when you might want to do this. One of the big benefits of doing this is speed. Migrating your API in this way allows you to very quickly realize the scalable, resilient, and cost-effective benefits that allows you as developers just to focus on your logic of your API and not worry about any of that scaling and failover. The second benefit is for you developers. Because we've added an additional class to our project, it means you can still develop and test against the API locally as you are used to. If I was to start up that API on my laptop, it would use the Kestrel hosting model that .NET APIs always use, and it's just when it runs in Lambda, we're telling Lambda to use that entry point class. This removes the need to learn the new Lambda programming model that we'll come on to in the next couple of slides, and it keeps you using a really familiar development experience. This does come with a trade-off though, doing things in this way. Running a Lambda in this way will have an impact to your cold start performance. And there's two reasons for that. The first is that your API actually needs to be bootstrapped. So in that initialization phase of a new execution environment, then the Lambda service needs to download your function code and then actually start up your API. So if the startup of your API takes a second, that's likely to make your code starts at least a second. And the second is around the bundle size. It's highly likely that an API packaged in this way will have quite a large bundle size. And that bundle needs to be downloaded to the execution environment for your function to execute. So the bigger that bundle size, that again is going to have an impact on code starts. From some benchmarking I've done for a moderately sized API, I've seen the execution time sit in around the 1.5 second range, with including a cold start. So it's by no means 5, 10, 20 seconds, but for really latency sensitive workloads, running an API on Lambda might not be the best approach. The second downside to running your Lambda functions in this way is that you kind of lose that fine-grained control both around security and resources. If you have an API with 4 endpoints, one of which is really resource intensive, let's say it needs a gigabyte of memory, but the other 3 are really lightweight, they only need 128 meg of memory, well then you're going to have to allocate all 4 endpoints the same amount of resources. This means that your lightweight endpoints are being charged per millisecond based on that gigabyte of assigned memory. And this also applies from a least privileged security perspective. So we talk a lot about the principles of least privilege at AWS. If you build your APIs in this way, every single endpoint on your API needs to have the same permission set, as opposed to giving each endpoint the least privileged permissions that it needs to do its work. One thing I will point out about both of these downsides is that these same downsides apply if you were running your application on EC2 autoscaling. You would still have a startup impact if your autoscaling group scales. There is that, what I would say is a cold start of your new EC2 instance. And you also have the same security and resources in that you have to give your EC2 instance all the permissions that it needs. And you'd also have to give it enough resources to cope with that completely variable load. One of the really powerful benefits of having the execution environments in Lambda is that each execution environment gets its own completely segregated resources. So if you assign a gigabyte of memory to a Lambda function, each individual execution environment will get its own gigabyte of memory. That means every single request that hits your API is guaranteed to have exactly the same amount of resources available to it. Again, looking back to EC2, if you're running the same application on EC2 and that EC2 instance is under a lot of load, all of the resources on that EC2 instance are shared between every single request. So you can get a really consistent level of performance with Lambda because you can guarantee the amount of resources that each API will have available to it. Okay, so now we've got our API running on Lambda, but what about if we want to start to take on more of this event-driven reactive programming model? Well, that's where we start to talk about single-purpose functions. If we were to run a similar API using single-purpose functions, it'd look something like this. We'd have a separate Lambda function per endpoint, and the routing to the correct Lambda function would be handled by API Gateway. So instead of having that single greedy route on our API gateway, we'd have 5 separate routes, and then we'd have 5 separate integrations to Lambda functions. We can also still connect them to a database, so we could still have maybe RDS sat behind the scenes. One thing I will point out here is that if you're using SQL Server on RDS, you need to be careful with how your Lambda functions scale, because it's highly likely that your Lambda functions will scale more quickly than the number of connections that your SQL Server can handle. Remember, each invocation of a Lambda function may well be in a separate execution environment, which will create its own separate SQL connection and its own separate communication with the database. So that's just something to be wary of as you move to start using Lambda, just to not overload your SQL Server database. So what does a Lambda function actually look like when you're building it in this way? Well, it's just a class. A Lambda function is just a class, and you need to have a single public method that is used as the handler. This method can be called absolutely anything. It is normally good practice to call it handler or function handler. And it's that handler that will tell the Lambda service to invoke for every single request that comes in. Everything outside of that function handler, or any methods that aren't called by that function handler, is what we'd call the initialization code. And that's the code that will run once per execution environment. The Lambda service requires a public parameterless constructor to actually create the class to invoke. And like I said, any initialization you do outside of that handler will run once per execution environment. And we'll talk about that a bit more when we get on to optimizations. Outside of the handler and the initialization, that handler method can take up to 2 parameters. The first parameter of our handler method will be the input, will be the event payload that the Lambda service passes to our function. And that event payload is always in a JSON format. The second parameter is an optional one, and that contains contextual information about that specific invocation. One of the benefits of using .NET with Lambda is that we can actually define a Lambda serializer, and you can see that at the top of the code sample there. We're defining a Lambda serializer, and we're saying to use a default system text JSON serializer. And what that means is that on our behalf, the JSON payload that comes in will get deserialized into an actual strongly typed object. So in this instance, we've got a custom class of hello request, and you see the input to our function handler, the first parameter, is just a hello request. It's a C# object, and that deserialization will be handled without us needing to worry about it. The Lambda supports both system text JSON and Newtonsoft based serializers. There's NuGet packages for both of them, and you can also define your own custom serializer. And the same applies for the output. In this instance, we're returning a hello response. That same serializer that we defined will be used to serialize the response back to a JSON string that will then go back to whatever happened to call this Lambda function. And there's a wide range of NuGet packages available that contain pre-built strongly typed objects for some of the common event inputs. Things like API Gateway, SQS, S3, Kinesis. There's libraries for all of these event types, which means Lambda can handle that serialization and deserialization on your behalf, and you're just working with a plain old C# object. So dependency injection is something that's widely used in .NET. It's kind of baked into the runtime really, and if you're building .NET 6 applications, you're likely to be using dependency injection in some way. And you can use dependency injection in Lambda in exactly the same way you would. So if you're building .NET APIs applications today, the screenshot on the left will probably be quite familiar to you. That's the startup class. We have the configure services method, and that's where we set up our dependency injection. We might load some configuration, do some setup logic, but there's some boilerplate code that's hidden away behind the scenes. The creation of that service collection, the setup of the service provider, that's all done by the runtime. So in Lambda, all we need to do is kind of bring some of that boilerplate code to the forefront. So as you can see on the right hand screenshot, that middle section where we're setting up our DynamoDB client, that is exactly the same. That's just copy and pasted from my .NET startup class. And all we're doing around that is manually creating the service collection, and then we're building the service provider when we're done with our configuration logic. And then we just expose that service provider as a static property on our startup class. When we actually come to use that within our Lambda function now, you can see on the right hand screenshot there, in our public constructor, we're just running that startup.init method. And then if you look in the internal constructor, and I'll get onto why there's a public and an internal constructor when we talk about testing, but we either use the DynamoDB client that gets passed in, or we grab the one from our dependency injection container. And if you compare that to the code on the left, which is how you would build an API controller in a .NET API, the code is almost identical, especially if you look at the controller, the endpoint body, the HTTP GET method. That is identical. So it's really easy to start migrating your .NET APIs or even any other .NET application to Lambda, and you can still use a lot of the familiar programming models that you're used to. A new library that's currently in preview is the .NET Lambda annotations framework, and this makes building .NET Lambda functions even simpler. It brings that programming model closer to what we are all used to as .NET developers. So if I start with the screenshot on the right, if you were building a Lambda function that took a request from API Gateway, you see we have to check the path parameters, check to see if they exist. And then down at the bottom there, we need to build an API Gateway proxy response object and set the status code for what is actually a really simple piece of code. All we're doing is adding two numbers together from the path parameters. If we built that same function with the Lambda annotations framework, you can see that on the left. All we do is annotate the method with an attribute to say this is a Lambda function. And then we also say this function is going to be a HTTP API. And then we say the method and the path for that API request. And then our actual function code is just our business logic. We focus right in on exactly what we need our business logic to do. In this case, add two numbers together. And this actually uses .NET source generators behind the scenes to actually generate that boilerplate code that wraps around this at compile time. It's available with the .NET 6 managed runtime, so if you're running Lambdas on .NET 6, this is available. And what it can also take care of synchronizing the Lambda function in handler code with a CloudFormation template. So we can start to generate some of that CloudFormation for you. It also makes it really easy to configure and consume dependency injection. So in the same way we annotated a method with a Lambda function attribute, you can also annotate a class with a startup attribute. And that will tell the Lambda annotations framework that that class should be used for our startup logic. And then in our function handler code, we can inject a service into our method. And the Lambda annotations framework at compile time will set up all that boilerplate code for us, so we don't need to worry about it. It really simplifies the development experience and brings it a lot closer to what we are all used to as .NET developers. Okay, so let's talk about development tools now and how you can actually get on and develop Lambda functions. Well, AWS provides toolkits for all of the major IDEs. So in Visual Studio, VS Code and JetBrains Rider, you can actually install an AWS toolkit. And for Lambda functions, these AWS toolkits provide a whole range of different features, including creating new projects, local debugging of your Lambda functions, and you can pass in event payloads. Some of them support remote debugging, so you can actually debug against a Lambda function running in the cloud. And of course, the nice right-click publish deployment experience that we're all used to in .NET. So from Visual Studio, I can right-click my project and say publish to AWS Lambda, and that will go off and publish it. There's also some built-in tools to the .NET CLI. So if you install the Amazon Lambda tools package in the CLI, the .NET CLI, you get some additional helper methods from the CLI. So there's a lot of different templates that have been built. So if you want to get started on Lambda really quickly, you can just do a .NET new and maybe initialize a serverless empty function project, and that will give you an empty Lambda function that you can then work with. You can also actually package, build and deploy your Lambda functions from the CLI as well. So there's a .NET Lambda deploy function, CLI command, that will then actually deploy your Lambda function code to AWS Lambda. This works really well either in Visual Studio or with the CLI. This works really well for proof of concepts and smaller projects, maybe as you're just getting started, but these Lambda functions don't often exist in a vacuum. You might have 4 or 5 Lambda functions you need to package together, maybe with an API gateway in front of them and a DynamoDB table behind. You want to do that all as one execution really. You don't want to be running 4 separate .NET Lambda publish commands from your CLI. You want that to happen all at once. So that's where we're going to move past these templates and past these right-click publish, and we're going to get on to production ready serverless with .NET. And to be production ready, a logical place to start is with testing. So developing and testing single purpose functions requires a bit of a change for developers. Serverless applications often integrate with a wide range of other AWS services, and whilst it's possible to emulate some of these services on your local machine, we should only really be doing this in edge case scenarios. The mantra I kind of say is don't bring the cloud to your machine, take your application to the cloud. And what that means is you should unit test your business logic locally. Write the unit tests in the same way you always have. Mock out your implementations and write really fast unit tests. But everything else, integration tests, load tests, performance tests, do all of that against cloud resources. Don't be trying to emulate DynamoDB locally, run your commands against DynamoDB in the cloud. And because this is serverless and you only pay for what you consume, the cost of DynamoDB for your integration tests will likely be quite low. When it comes to unit testing a Lambda function, this is why we have the public constructor and the internal constructor, because this enables us now to inject mock implementations into our Lambda function. Remember, we need that public parameterless constructor for the Lambda service, so we have to have that. But then we've got this second internal constructor that we can use to inject mock implementations. So we can expose that internal constructor to our unit test project and then actually mock out any implementations or interfaces that our Lambda function needs. And we can do that to test our business logic in our Lambda function without worrying about other AWS services and our integrations. But as I said, when it comes to integration tests, you want to be doing this against cloud resources. And to do that, let's talk about how we'd actually go about deploying our functions. And we'll actually look at a tool that you can use to really quickly synchronize your local code to the cloud. And there's a large number of frameworks you can use to actually build serverless applications. There's two provided by AWS, the Serverless Application Model and the Cloud Development Kit. And then there's a few open source and third-party tools like Terraform and the Serverless Framework. For this presentation, I'm going to focus mostly on AWS SAM. But if you are interested in the CDK, I've got another talk later today covering building event-driven architectures with .Net and the CDK. So check that out if you're interested in the CDK. There's two parts to AWS SAM. The first is some extensions and helpers on top of CloudFormation that makes it really easy to define Lambda functions. So if you're familiar with CloudFormation, this will be quite familiar to you. The interesting ones I'll call out from a SAM perspective are the policies. So the policies are some pre-built IAM policies that abstract away you needing to remember which actions and resources you need to do a certain thing. So in this instance, this function needs to be able to read from DynamoDB. So we just add a policy of DynamoDB read policy. And when we actually build this SAM template now, SAM will actually convert that into the IAM actions required for our function to be able to talk to DynamoDB. The second interesting thing that SAM does is that if I define an event for my Lambda function that is an API, as we are doing here, SAM will actually automatically go and generate the CloudFormation for API Gateway and create all the routes and interfaces required. It will do that automatically without us doing anything. Then you can see down at the bottom there, we're actually creating a DynamoDB table, and SAM has this helper type of simple table, and that will just create you a DynamoDB table with a partition key and some sensible defaults. So you see in 19 lines of code there, we've defined a serverless API, albeit with only one endpoint. The other part of the SAM CLI is the CLI, and there's a few really interesting commands on the CLI that you can use to really quickly get started and build your serverless applications. The first is SAM init. SAM init lets you initialize a new SAM project from a set of templates, of which there are a number for .NET. SAM build is what actually compiles your code and gets that ready to be deployed. SAM deploy then actually deploys your function to the cloud. But the really interesting one from a testing perspective is the SAM sync command. So if you run the command SAM sync with a watch flag, that actually sets up a file watcher to automatically sync changes from your local machine to the function deployed in the cloud. And when you use SAM sync, it actually talks directly to the Lambda APIs. It doesn't go through CloudFormation, which means it's incredibly quick to redeploy changes to your Lambda function. When you run SAM build, what SAM does is looks at each function resource in your CloudFormation template, and then for each function it runs a .NET publish command, and then packages up the output of that publish command into a zip file. So you can actually go and look after you've run sam build, you can actually go and find all the packages for your functions. When you then run sam deploy, that uploads your zip files to S3 and then creates the CloudFormation stack to actually deploy your functions. And you can actually see in the CLI the status of what CloudFormation is doing. Okay, so now we've got applications built and deployed and we're production ready. So let's now quickly talk about some best practices and optimizations. The first is around observability. Observability is really important in serverless applications because each component of your app is completely self-contained. It's incredibly distributed. So having a good strategy for observability is really important. The first is around logs. Ensure that you use a structured logging format. So anything you write to the console in Lambda will be forwarded straight to CloudWatch logs. But if you use a structured log format, if you create your logs in JSON, for example, you can then query your logs across all of your functions. The second is tracing. And if you've got tracing enabled in your Lambda function, that will actually generate X-ray trace ID. And then you can auto instrument your functions to actually monitor and pass that trace ID around your systems and see how your applications talk to each other, the parts of your application talk to each other. And the final one is metrics, and metrics both from an infrastructure perspective, so the invocations of your Lambda, the errors of your Lambda functions, the latency, things like that, but also business metrics, how many orders have been created, how many users have signed in. All of them are really important for a good observability strategy. With X-Ray, you can configure auto instrumentation for your traces for things like the SDK calls, for calls to SQL Server. So you can see here, I'm making a call to register X-Ray for all AWS services. And then any SDK client I create after this line of code will be automatically instrumented by X-Ray. So my DynamoDB client there that I'm creating on the line after will be automatically instrumented without me doing anything. And I can go and look at that in the X-Ray console. I also want to quickly talk about Lambda Power Tools for .NET. So Lambda Power Tools is currently in alpha, and it's a suite of utilities that enable you to use best practices. It currently supports logging, metrics and traces. And to do that, you can add some really simple helpers. So you can see we're capturing metrics on cold starts just by adding an attribute to our function. We get a static logger object as part of the library that allows us to create structured logs really easily. When I create a log using this static logger, it will automatically inject into that structured log things like the service name and some request specific context. And the same applies for tracing. We get a static class for tracing certain parts of our application. So I'd really encourage you, if you're adding observability to your Lambda functions, to go and check out Lambda Power Tools. The second thing is the optimizing for cost and performance. So there's a really awesome tool called AWS Lambda Power Tuning, which allows you to run some analysis on your Lambda functions and find that right balance between cost and performance. And it actually gives you a graphical output that you can then look at to really find that sweet spot for your specific Lambda function. When it comes to optimizing your application code, you need to make sure you define shared objects outside of your handler. You don't want to be initializing a new DynamoDB client for every single request that comes in. Do that once per execution environment and reuse it across each invocation. And the same applies for connection strings, any secrets management, things like that. Load that all up at initialization time and then reuse that across invocations. Okay, I teased this at the start, but let's get back to cold starts, because cold starts are the common thing that have put people off using .NET on Lambda. So I've done quite a lot of benchmarking with .NET on Lambda, and to do that we have a set of samples on the AWS Samples GitHub that use the same application architecture across different programming languages to give almost a like-for-like comparison of runtimes. So this API is a simple CRUD API that just talks to DynamoDB. And this, what you can see on screen here, is the performance both of .NET and of Go. So you can see if I'm running a full API on Lambda, the minimal API row, I'm getting a cold start invocation time of about a second, 1.2 seconds. Whereas if I then look at .NET 6 and I use .NET 6 with native AOT, I'm getting a performance characteristics similar to what Go is getting. And this is actually faster than TypeScript. If you're interested to go and have a look in more detail at this benchmarking, you can go and look at the GitHub repo that you can see on the screen there. But it's getting closer and closer. These compiled languages are getting faster and faster, and they're becoming a more realistic option when compared to some of the interpreted languages. And that's enabled by native AOT. So native AOT is a feature in preview in .NET 6, and it's going GA in .NET 7. Native AOT generates platform-specific code at compile time, and that gives you a set of binaries that can be executed without the runtime being installed. Also, as the code is pre-compiled to be platform-specific, it also has a substantial performance impact, and this performance improvement directly impacts .NET applications running on AWS. There are downsides to doing this though. The application must be compiled on the same OS and architecture that you're going to deploy to, which means you have to compile your Lambda functions with native AOT on Amazon Linux too. And there's ways you can do that using Docker files. If you're interested, come and catch me after the talk. It also increases your build times slightly because the compiler is actually compiling to a specific OS and architecture. It does actually increase your build time. And using native AOT does quite a lot of trimming to your application. So things like reflection and dynamic assembly loading, and also any libraries that aren't particularly trim friendly, you might find that the native AOT compilation trims out some code that your application actually needs to function. And that's seen really directly if you're doing any kind of serialization. So the backbone of nearly all .NET serializers is reflection. And reflection is great in quite a lot of scenarios, but not when you're trying to do high performance cloud native application. It's a problem for startup, memory usage, assembly trimming. So if you're using native AOT, you need to be looking at source generated serialization. And source generated serialization uses .NET source generators to generate the code for serialization and deserialization at compile time. It actually generates a static model at compile time to access data on the types, and it uses optimized serialization logic. When you're doing that though, you need to ensure you tell your serialization context the objects that it needs to generate that serialization code for. So you can see here there's 4 objects that I'm asking the source generated serializer to actually use and generate that static serialization code for. A product wrapper, and then my proxy request and response. When I also define my Lambda serializer, I also need to define that as a source generated Lambda serializer and pass in my serialization context, and that way Lambda can then use my custom source generated serializer. And the final thing I'll just touch on really quickly is Lambda layers. So layers are a feature of Lambda that allow you to share code. So you can generate a layer, and that actually reduces the size of your compiled binary. So you can do this with .NET, but ordinarily it's not really recommended. It does add quite a lot of complexity to your build process, because you need to first generate the Lambda layer, deploy the new version of the layer, and then compile your Lambda function telling it about that new version of the layer. It also uses the .NET Store CLI command, which is a CLI command used to generate runtime package stores, but that .NET Store command is not actually being maintained by Microsoft anymore. So you can look at Lambda layers, but ordinarily for the compiled runtimes .NET and Java, it's not normally a recommended approach. Okay, so is Lambda the right fit for my workload? Let's just finish on this. And in almost all cases, the answer is yes. There are a couple of reasons why Lambda might not be the right fit. Remember, if you've got a workload that needs to run for longer than 15 minutes, Lambda can't really support that. And if you've got a stateful workload, let's say you do a lot of work in memory for performance reasons, again, because Lambda's completely stateless, that may mean you either need to refactor to change your programming model or look at some other way of running your application. Other than that, Lambda can support almost any kind of workload with the right configuration. And even with the conversation around cold start, if you compare that to the cold start of a EC2 instance or a container, it actually becomes a really convincing way of running almost any kind of workload. So what next steps are there? What can you do as you leave this talk? Well, the first is to go and try things out, go and build a Lambda function. Download the SAM CLI, run SAM init, and see just how powerful serverless technologies can be. Thank you.